Hello everyone, this is lecture 11 of ComSci 142, All Pairs Shortest Paths. In this video, we will discuss two all-pair shortest paths algorithms, which are the Floyd-Warshall and Johnson's algorithm. So first, let us recall the all-pair shortest paths problem. As an input, we will get a weighted graph G, and for the output, we will try to find the shortest path for all pairs of vertices in the graph. So you will have to do this for all vertices to all other vertices, okay? So all pairs of vertices. Take note that we don't have a source vertex unlike in single source shortest paths. Because we're doing this for all pairs, then we don't really need a source vertex. And if a negative cycle exists in the graph, the negative cycle should also be detected, because in that case, no shortest path can exist. Okay? Now, let's answer this question. How many invocations or how many runs of an SSSP algorithm are needed to solve a PSP? Is it 1, n minus 1, n, or n squared? So try to think about the answer first before moving forward with this video. In fact, we will need n runs or n invocations of an SSSP algorithm to solve a PSP, which would be ones for each vertex as the source. Okay? Now, can we do better than this? Well, it actually depends on the graph. So, let's check the conditions of the graph. Does the graph have negative edge weights? Is the graph sparse or dense? Okay? Because based on those conditions, we will be able to tell whether we can improve on running an SSSP algorithm n times. Okay? So, if we have non-negative edges, that means that Dijkstra's algorithm, which could be run in O of m log n using the heap data structure, if you run that n times, then n times O of m log n would be mn log n, right? Now, let's check if the graph is sparse or dense. If the graph is sparse, meaning that the number of edges m is just O of n, okay, so it's close to the number of vertices, then if you plug in n here as the value of m, mn log n will become n squared log n. However, if the graph is dense, where m is n squared, okay, so if you plug in n squared here in place of m, this would be n squared times n, or n cubed. So on a dense graph, running Dijkstra's algorithm n times would take n cubed log n. Okay, so it's there's a difference in the running time when it's a sparse graph versus if it's a dense graph. Now, if we have negative edges in the graph, then we cannot use Dijkstra's, right? We're forced to use Bellman-Ford because that is the general algorithm. Okay, and remember that Bellman-Ford runs in O of mn. Now, if we run Bellman-Ford n times, so n times mn would be n squared m. Now, if you had a sparse graph where m is O of n, so this m would become n, so this will be O of n cubed ang running time if it's a sparse graph. But if it's a dense graph where m is also O of n squared, so that would be n squared times n squared, the dense running n times Bellman-Ford would take O of n to the fourth power. Okay? So, it would also take a longer time. So, it depends on the graph, okay, whether it has negative edges or not, and whether the graph is sparse or dense. Okay? So, let's see the first APSP algorithm, which is the Floyd-Warshall algorithm. So, it's an APSP algorithm that runs in O of n cubed. So, it's better than some algorithms here than just running an SSSP algorithm n times. So, if it's n cubed, then it's better than this one, right? Because this is n cubed log n, but it's not better than this one because n squared log n is better than n cubed. It's also better or equal than this one, and then it's better than this one definitely, right? So it can beat running Dijkstra's or Bellman-Ford n times. So it's an APSP algorithm that runs in O of n cube, and it uses dynamic programming technique. Okay, so remember or recall your dynamic programming techniques. So we'll have to do sub-problem recurrence relations, and then we'll do the tabulation. Okay, so this algorithm will work even if there are negative edge weights in the graph. So we don't have to worry whether the graph has non-negative edge weights like in Dijkstra's. Okay, so how does before we talk about how it works, a little bit of history. This algorithm was discovered independently by different people, by Bernard Roy in 1959, by Robert Floyd in 1962, and by Floyd-Warshall in 1962 as well. Sometimes it's also known as Roy-Warshall and Roy-Floyd algorithm, but it's more popularly known as the Floyd-Warshall algorithm. Okay, so how does it work? So we mentioned that it's a dynamic programming algorithm. So we will have to think about what the sub-problem is, right? Since that's how dynamic programming works. So our original problem is finding out the shortest path from A to B. So those two vertices. So a smaller sub-problem would be the shortest path from A to B, but you can only use certain nodes in the path. So you'll try to restrict which nodes can be used in the path from A to B. Okay, so that would be our smaller sub-problem. Okay, so the original problem would be from A to B using any vertex as intermediate nodes in the path. But for smaller sub-problems, we will restrict which nodes can be placed in the intermediate nodes. Okay, so what we will do is we will order the vertices arbitrarily from 1 to n, but usually what we'll do is just we'll order them alphabetically. So if you have A, B, C, D, E as the vertices, then we'll just label that 1 to 4. Okay, so let V raised to k be the vertices from 1 up to k. So whichever vertices you labeled 1 up to k, they will be part of this set V raised to k. Okay, and our sub-problem would be denoted by SP of A, B, K. So this sub-problem means that it's the shortest path from A to B, where all the internal nodes are part of the set V raised to K. So meaning, you can go from A to B, but you're only using these nodes here as internal nodes, meaning you can pass through them. Okay? So, to make this clearer, here's an example. Okay. So, in this graph, what is the shortest path from A to B? So, without restrictions, the shortest path from A to B is if you take the path, the bottom path, right? So, AEB, A to E, E to B, this would cost negative 20 na path. So, this is the best one. Okay? However, if you restrict it to SP of AB4, and let's say that we label this 1, 2, 3, 4, and 5. So, we label them alphabetically. If we restrict it only to SPAB4, that means that what is the shortest path from A to B, but using only vertices A, B, C, and D as the intermediate nodes in the path. So in this case, we cannot use E anymore since it's not part of this set. So we cannot take this path, okay? It's not possible. Instead, we are forced to choose the upper path, which is 2 minus 4, so negative 2, plus 5, which is 3. Right? So, if we're restricting it from A to B using only vertices from A to D, then the shortest path would only be 3. Right? So, ACDB. That would be the path. Okay? So, that is how we will formulate our sub-problems using or restricting the shortest path, restricting it on based on which nodes you can use along the path. Okay, so how will we represent, or how will we express this subproblem in terms of smaller subproblems? Because remember that in dynamic programming, you have to form the recurrence relation, right? So express this subproblem in terms of smaller subproblem so that you can tabulate it easily. So consider the subproblem SPABK. Now the shortest path of A to B could either go through vertex K, meaning the last among the set, or not. Okay, so it could either not go through K or go through K. So those are the two cases, right? So what would happen if the shortest AB path does not go through the last vertex K? Then that means that you're only using vertices from 1 up to K minus 1, since you're not including the vertex K, right? The last vertex. So that means that you could express SP of ABK to AB K minus 1 na lang, because anyway you're not passing through vertex K. So you can just use from 1 up to K minus 1. So this subproblem could just be the smaller subproblem's value right away. Okay? But that is if it does not go through vertex K. If it does go through vertex K, it would look something like this, right? Because the shortest path would pass by K and then eventually go to B. If it does go through K, since it follows dynamic programming, it should follow optimal substructure, right? Meaning the shortest path from A to B should contain within it shortest paths also. So the shortest path from A to B should contain the shortest path from A to K and from K to B. Okay, because if A to K is not the shortest path, then this A to B path is not the shortest path also, because there should be a shorter path to get to B without going through K. Okay, so if that is the case, then we will call this path 1, the path from A to K, the shortest A to K path, while using only internal nodes in VK minus 1, since we're not using K here, since it's already the destination, right? So these internal nodes here are from 1 up to K minus 1 lang. Whereas in P2, this would be the shortest K to B path. Okay, so from K to B, using also internal nodes in VK minus 1. So meaning you're not also using K because it's the source. So the nodes along this path would be from 1 up to K minus 1 only. Okay, so that if that is the case, then we will combine path 1 and path 2, because that goes from A to K and then from K to B. So the shortest AB path is path 1 plus path 2 if it does go through vertex K. So that would be the subproblems SP of A to K, and using only K minus 1 as the internal nodes, and from K to B using K minus 1 as the internal nodes, and then we'll add them. So this is the case for when the shortest AB path does go through vertex K. Okay, but however, we don't know which of the two is the right answer. So it could be that it doesn't pass through K, so this is the subproblem, so ABK minus 1. Or if it does go through K, this would be the subproblem, AKK minus 1 plus KBK minus 1. So since we don't know which path is shorter, we will solve for both and then take the shorter one. So we'll get the minimum. Okay? So that's it. We will just get the minimum of either this value or this value. Okay? So we can now tabulate everything, because our current subproblem's value can be based on the smaller subproblem's value. So in the tabulation, we will create a 3D array, because this will be indexed by A, B, and K, right? So remember that our subproblem is SP of ABK. So this is a 3-dimensional array. Okay? So pretty much mirrors the subproblem notation. The 3D array entry for SP of A, B, and K is the shortest AB path with internal nodes in belonging to the nodes from 1 up to K. Okay? So for the base case, remember that in dynamic programming we have to uh, fill in the base case values, because otherwise we can't solve for bigger subproblems without any prior values that exist in the table, right? So for our base case, that would be SP of A to B using 0 intermediate vertices. Okay, so no intermediate vertices. So if you can't pass through any vertex along the path, then we will just use the existing edges. Okay, so what we will do is we will write 0 along the diagonals, that is if A is equal to B. Okay, that is because if A is equal to B, then your source is also your destination, right? So that would be 0 along the diagonals. And then if edge AB exists, then we will write the weight of AB along this cell. Okay, because that is the immediate way to get from A to B, because there is an edge that exists. Okay, otherwise it would be infinity because it's unreachable. Okay, if there is no edge that connects them, it's infinity because you cannot reach A to B without any intermediate vertices. Okay, so this would be our base case. So we'll fill this up for all edges, and then along the diagonals we'll write zeros. For the rest, it would be infinity. Okay, so putting all of that together, this would be the pseudocode for Floyd-Warshall algorithm. So we'll initialize a 3D array, we'll call that SP, and then this part here, okay, so this part here is initializing the base case. Okay, so for A from 1 to N, for B from 1 to N, then you'll write AB0 is 0 if A is equal to B. So this is along the diagonal. If edge AB exists, then you'll write the weight of AB, and then otherwise it be infinity. So this is the base case. So the whole thing here is for the base case. Okay, and then this is the actual tabulation. So for K from 1 to N, for A from 1 to N, and then for B from 1 to N. And then SPABK is just the minimum of ABK minus 1. So this is from the previous table. And then AKK minus 1. So this has already been solved as well. Same with this one. Okay. So it's pretty straightforward once you have the recurrence relation for the subproblems. Okay. So let's try to analyze the algorithm for its running time. So for the base case, the upper or the outer loop runs in n iterations because it's from 1 to n, and then the inner loop is also n iterations, and then for the rest it's constant time since you're just checking and assigning values. So the base case is actually n times n, or n squared, right? And then for the actual tabulation itself, so this one, the outer loop runs in n, the inner loop also runs in n, and the innermost loop also runs in n. So that's n times n times n. That would be n cube. Okay, and then for inside, it's just constant time because you're just getting the minimum of two values, right? So just that's basic comparison lang. So that would be n squared plus n cube. So it's in O of n cube. So you mentioned that Floyd-Warshall runs in O of n cube. So that's why this is the running time, right? So that is the analysis for the Floyd-Warshall algorithm. So again, base case is O of n squared. Main loop is O of n cube because you have 3 for loops that are nested within each other. And each iteration takes constant time because you're just looking for the min. So the running time is O of n cube. And then of course for the memory, it's also O of n cube because you're using a 3D array that's of size n by n by n. Okay? Because here, you notice that A, B, and K runs from n, n, and n. Okay, so it's a n cube sized array. Okay? So, Floyd-Warshall algorithm, as it is, only computes for the shortest path lengths. Okay? For the actual paths itself, you will need to keep a backtrace, just like what we're doing in the other dynamic programming algorithms. Okay, and then to check if there's a negative cycle, we'll check the diagonal of the final table if there are negative values, and if there are, that means that there's a negative cycle. Otherwise, if it remains 0, because it should remain 0 if it's the shortest path, right? Because from A to A, or B to B, or C to C, you're already in the node itself, right? So the shortest path should be 0. So if there are negative values along the diagonal, then there's a negative cycle. So the reason for this is because using all vertices as possible intermediate nodes, an A to A path still has a negative value after doing a tour. So there is a cycle, a negative cycle from A going back to A. Okay, because there's a negative value. So if that's the case, there's a negative cycle, and the shortest path values are invalid. Okay. So for the example, we're given this graph here, and I actually made a separate demo video that will detail how Floyd-Warshall algorithm works. Okay, so just watch that video separately. I won't show it anymore in this video since that video is actually quite long. Okay, so it's because it's very detailed. Okay, so given this graph, what Floyd-Warshall algorithm will do, as you'll see in the demo, is that it will compute for k is equal to 0. So it will start with zeros along the diagonals, and then the rest of the values are the edge weights. And then for k is equal to 1, you'll just need to do the computation of either abk minus 1 or akk minus 1 and plus kbk minus 1. So you just need to compare, but I showed you a shortcut in the demo video, so please watch that. So these are the values for k is equal to 2, k is equal to 3, k is equal to 4, and then k is equal to 5. So this is the last one since you have 5 vertices. So this is the final APSP values for that graph. Okay, so again, please watch the demo video for the details of how we came up with these values. Okay, so that is Floyd-Warshall algorithm. Now, going back to running SSSP algorithm n times to solve our APSP problem, which algorithm will we prefer in using or running SSSP algorithm n times? Dijkstra's algorithm has a running time of m log n using a heap data structure, and Bellman-Ford is in mn. So if it's just pure running time, Dijkstra's runs faster, right? However, the problem is Dijkstra's is pretty limited because it only works for non-negative edge weights, right? Dijkstra's is faster, but it's limited to non-negative edges. So to be safe, we'll have to use Bellman-Ford. But what if we could reweight the graph so that if there are negative edges, we'll reweight the graph so that it becomes non-negative, and then we can use Dijkstra's n times. Okay? But remember in the last video when we did the reweighting, the wrong reweighting, that if you just add a simple constant value to each edge to make the edges non-negative, it doesn't work because there's an unbalanced reweighting of paths. So you don't actually conserve the or preserve the shortest paths. So we can't just add a constant value to all edges and call that the reweighting technique. Okay? So instead, what we'll do is we'll look at Johnson's algorithm, which creates a reweighting technique for a graph so that we can run Dijkstra's algorithm n times. Okay, so Johnson's algorithm was created by Donald Johnson in 1977. So it's an APSP algorithm that also works even if there are negative weights. Okay, it actually uses Bellman-Ford and Dijkstra's algorithm within the algorithm itself. So it's a application of the two, and as I mentioned, it uses a reweighting technique so that you can run Dijkstra's n times. So how does it work? Okay, so first, each vertex will have an associated value C. So we'll call this the score, or just the value of each vertex. And then we'll reweight the graph so that the edges become non-negative. So to reweight the graph, we will use this equation. So the new weight of AB is equal to the original weight of AB plus the score or the value of the source vertex A minus the value of the destination vertex B. Okay, so if it's A to B, you add the value of A and then you subtract the value of B to the original weight. So that is how we'll reweight it. Okay, so it will preserve the shortest path but not the path cost itself. So later on we'll have to readjust the path costs so that it becomes correct. Okay, so as an example of the reweighting, let's say that A and B has as an edge with weight 2, and A, let's say, has a associated value -4, and B has an associated value -3. So to reweight this, this is the original weight 2, and then we'll add plus -4, so that's -4, and then minus the value of B, so minus -3 is +3, so this becomes -4 plus 3 plus 2, so that becomes 1. So the new weight here will become 1 in the reweighted graph. Okay, so to do that, first we will have to add a new vertex S. Okay, so we'll add a new vertex S, and what we'll do is from this vertex S, assuming that there is no existing vertex S already. So if there's a vertex S, then you name it something else. So the idea is you just add a new vertex. Okay, so from this vertex, new vertex, you add an edge from S to all the other vertices with weight is equal to 0. So you're not actually affecting the shortest paths because anyway the weight is 0, right? So you could freely pass through these edges. And take note that edges should only go out from S, not go back in. So you're not adding any incoming edges to S, okay? Only outgoing edges. So after that, what we will do is we will run Bellman-Ford algorithm to solve SSSP with the source being S. And we will use Bellman-Ford because we're not sure about our graph. There could be negative edge weights at the start, right? So because Bellman-Ford allows negative edges to be solved, then we will use that one to be sure, right? To be safe. So with the source vertex being the newly added vertex S, we will run Bellman-Ford, and then we will get a shortest path value to all the other vertices, right? So what we'll get from Bellman-Ford, the shortest path from S to the vertex would be the associated value C of A that we'll use in the reweighting. So that is the score or the value that we'll use in reweighting the graph. Okay, so run Bellman-Ford, and then the shortest path from S going to those vertices, that would be the score or the associated value. So this new vertex S actually does not affect the APSP. Why is that? Because there are no edges going into S, so it can't be an intermediate node. So since S is only going outwards, okay, it can't be used as a intermediate node to create a new path or a new path that will affect the original APSP solution, right? So it should work. So after getting the associated values for each vertex, then you will have to reweight all of the edges using this equation that I mentioned earlier. And then after that, after reweighting, all edges will now be non-negative. And since it's non-negative, then we can use Dijkstra's n times to get APSP. Okay? So we'll use n runs of Dijkstra's, one for each vertex as the source. So if you have 4 vertices A, B, C, D, so the first run will use A as the source. So that would solve for A to all the other vertices, and then the next run would be B as the source. That's B to all other vertices, and then C as the source, and then D as the source. Okay, so then you will get the all pair shortest paths because you ran Dijkstra's n times. Okay, so after that, we're not yet done because since we did Dijkstra's on the reweighted graph, the shortest path values that we got is actually not the correct shortest path lengths because we reweighted the graph. So we'll have to readjust the shortest path lengths back to their original path lengths, okay, or path costs. So to readjust, what we will do is the shortest path of AB here, you will subtract C of A, or the associated value of A, and then you add the associated value of B. Okay, why will we do this? Because earlier, when we reweighted the graph, you added CA and you subtracted CB, right? So, to rebalance it, we'll have to subtract CA again and add back CB. So, you're just doing the opposite of what you did in the reweighting. So, in the readjusting, you will have to reverse the reweighting that you did. So, after doing this, you'll get the actual shortest path lengths, or the correct shortest path lengths. Okay? So that is Johnson's algorithm. So putting all of that together, we have this pseudocode. So first, you'll need to add a vertex S, and for each vertex in the graph, we'll add an edge from S to that vertex with weight 0. After that, we will get the SSSP Bellman-Ford starting at S, and the path lengths from S to the vertices would be our associated value C for each vertex. We'll need to stop if the Bellman-Ford algorithm found a negative cycle, because remember that Bellman-Ford can do that. So if it found a negative cycle, then there's no point in finding APSP, right? But if there's no negative cycle, we'll continue. For each edge, we'll reweight each edge using this equation, and then for each vertex A, we'll run Dijkstra's with A as the starting vertex, right? So after that, after running Dijkstra's n times, we will readjust all of the shortest path lengths using this equation again. Okay, so after that, you'll get the actual correct answer. So let's try to analyze the running time of this algorithm. So for each vertex A, so you'll do this for each vertex, right? So that would be O of n, because you're doing it once for each vertex. And then Bellman-Ford, remember, runs in n. Okay, so mn ang Bellman-Ford, so it will run in mn. And then for each edge, we'll reweight the graph. So this will be in O of m, because it's once per edge. And then this one is for each vertex, so that's one for each vertex, so that's n. And then Dijkstra's runs in m log n, right, if you use a heap. So total of this here is nm log n, because that's n times m log n, right? And then for this one, for each vertex A, and then for each vertex B, so this is n times n, this is n squared. So in total, that would be n plus mn plus m plus nm log n plus n squared. So which is the biggest term here? It's actually nm log n. So the running time here is O of nm log n. Okay, so yeah, so adding vertex S, O of n, one Bellman-Ford is O of mn, reweighting takes O of m, because you do it for each edge. Dijkstra's run n times is nm log n, and then you adjust this shortest path lengths, it's n squared, so the running time is mn log n. Okay, yeah, then running time is mn log n. So if it's a sparse graph where m is O of n, the running time is n squared log n. And on sparse graphs, it's better than Floyd-Warshall, which is O of n cube, right? Because n squared log n is better than n cube. But on a dense graph, this would become m here would become n squared, so this would become n cube log n. So actually, Floyd-Warshall will run faster if it's on a dense graph. But on a sparse graph, it runs better than Floyd-Warshall. Okay? So, yeah. So, for the example, I also showed this in the demo video, the separate demo video. So please watch that again for the details of how this graph was solved using the Johnson's algorithm, the APSP problem. Okay, so I'll just show you the results. So if you get the shortest path from S, the newly added vertex S using Bellman-Ford, this would be the shortest path lengths. So this would be the scores. So what you'll do is you'll reweight the edge using those scores. After you get the reweighted edge, you'll run Dijkstra's algorithm n times. So these are the results, and then you will need to readjust the path lengths. So after that, you'll get this shortest path lengths for that graph. Okay, so again, please watch the demo video because I also showed you like a shortcut of how to readjust and compute the distances, or do the reweighting and readjusting quickly. Okay, so I showed you a shortcut in that demo video. Okay, so that's it for Johnson's algorithm. And so to review, for this video, we discussed two algorithms for APSP. So the first one was Floyd-Warshall, which was a dynamic programming algorithm. We just expressed the shortest path problem from A to B in terms of smaller subproblem ABK, which means that you're only restricting the internal nodes from 1 up to k, assuming that you labeled them arbitrarily. Okay, so SPABK is min of ABK minus 1 if it doesn't pass through k, or AKK minus 1 plus KBK minus 1 if it does pass through vertex k. So this is the shortest path from A to k. This is from k to b, okay, using only internal nodes from 1 to k minus 1. So just do that, do the tabulation, and then should solve the APSP problem. And then for Johnson's, what we did was we added a vertex S, and then add an edge for each from S to all other vertices with weight 0, and then run Bellman-Ford using S as the source, and then use those shortest path lengths as the score for the reweighting. And then after that, you'll use the reweighted graph and run n times Dijkstra's algorithm, one for each vertex as the source. And then you'll have to readjust the shortest path lengths because the current lengths are for the the reweighted graph. So readjust it, counter what you added and what you subtracted earlier in the reweighting, and then readjust it back to their original lengths. After you do that, you get the APSP solution. Okay, so that's it for this video. If you have any questions, please don't hesitate to ask, and I will see you in the next video.